Welcome to part 2 of our help video for Calculusthenics number 2. What I'm going to do in this video is work numbers 5 through 9, part A of all those problems, and hopefully that will help you with the part B problems. So let's take a look at this first number, number 5A. We're looking at a rational function, and I want you to notice that the numerator is a polynomial and the denominator is a polynomial. So we can examine degrees of the numerator and the denominator and make decisions about how this function behaves on the ends. And what we're interested in, since x is approaching positive infinity, we're interested in how this function behaves at the right end. So what you'll notice is that the degree of the numerator is larger than the degree of the denominator. Okay, so let's think about that. As x is getting bigger and bigger and bigger, this numerator is going to get larger, the denominator is going to get larger as well, but since the numerator has a higher power, it overpowers the denominator, and so that makes this quotient grow without bound. So we're going to say that the limit as x approaches infinity of this ratio is positive infinity, but I want you to write some kind of rationale so I know how you got that answer. So all you need to say is that the degree of the numerator is greater than the degree of the denominator, and that will be enough for me to know why you know that this function grows without bound as x approaches positive infinity. Now let's take a look at number 6a, and you'll notice that this time the degree of the denominator is larger than the degree of the numerator. So as x is approaching infinity, both the numerator and denominator are getting larger, but since that degree of the denominator is larger than the degree of the numerator, that means that the denominator is going to grow a lot faster. It's more powerful. So if you have a ratio where the denominator is much larger than the numerator, then that function will approach 0 as x approaches infinity. So we're going to say that this limit is equal to 0, and then I want you again to write some type of rationale. So let's just go ahead and say that the degree of the denominator this time is greater than the degree of the numerator. And then it might be worth noting, you would need to write this down, but since this x squared term is negative, the limit of this function would approach 0, but it would be approaching 0 from below the x-axis instead of above the x-axis. In number 7, let's go ahead and examine the degrees of the numerator and denominator. So if you notice the numerator, the highest power of the numerator is this final term, its degree is 2, and then in the denominator the highest power is this first term, another degree 2. So here we have a rational function where the degree of the numerator is equal to the degree of the denominator. So that means there is a horizontal asymptote that determines how this function behaves at both ends. So it doesn't matter whether we're going to positive infinity or negative infinity, the graph will approach the same horizontal asymptote. And to find that horizontal asymptote, we look at the leading coefficient of the numerator, which I know we call it the leading coefficient, but that doesn't necessarily mean it's the first term. The leading coefficient will be the coefficient of the term with the highest degree. So we have a leading coefficient of 3 on top and a leading coefficient of 1 on the bottom. So that means that this graph has a horizontal asymptote at y equals 3 over 1, and therefore the limit as x approaches negative infinity is approaching 3. So again, the only rationale you need to write is that the degree of the numerator, oops, that's an E. Well, let me write that again. The degree of the numerator is equal to the degree of the denominator. So let's take a look at number A, and this time we have a new type of function. You'll notice this time we don't have a rational function that we're dealing with. We're looking at an exponential function. So let's think about how this function behaves, how the graph of this function behaves as x approaches negative infinity of the function 3 minus 2 to the x. So you might notice that this exponent of x will always be, as x approaches a negative infinity, these will most likely be negative numbers. So I just want to remind you of a property from Algebra 1 that says if we have something raised to a negative exponent, like a raised to the negative a raised to the negative n power, that's the same thing as 1 over a to the positive n power. So as we're looking at these 2 to the x values, as x gets more and more negative, we're really looking at 1 over 2 to some positive number, and this positive number keeps getting bigger and bigger and bigger, which means 1 over 2 to that positive number is 0. So in other words, the limit of this function as x approaches negative infinity of 3 minus 2x, as x gets more and more and more negative, that means this is approaching 3 minus 0, which is equal to 3. So now I just want to show you another way to check your answer. Let's think about what's going on graphically. So what I'm going to do is I want to eventually end up with the graph of 3 minus 2 to the x, but let's do it in steps. Let's start by just sketching the graph of y equals 2 to the x, which would look something like this. So this is the graph of y equals 2 to the x. That's 2 to the x power, which would pass through the point 0, 1. Now let's sketch the graph of y equals negative 2 to the x, which would be a reflection of this graph in the x-axis, so it would look something like that. So this is the graph of negative 2 to the x. And then last but not least, let's go ahead and graph this 3 minus 2 to the x. I'm going to rewrite that, though, as negative 2 to the x plus 3. So you can see that that is just going to be the graph of this function, negative 2 to the x, has been shifted up 3 units. So what I'm going to do is I'm going to take this horizontal asymptote of y equals 3, and I'm going to shift it up 3 units, 1, 2, 3. So here's my new horizontal asymptote, and then take the graph of negative 2 to the x and just shift it up 3 units, so it would look something like that. So now we can see that as x is approaching negative infinity, we can see that this blue graph is getting closer and closer and closer to positive 3, which just confirms the analytical work that we did right here. And then last but not least, let's take a look at number 9a. Now this time our function is a ratio, but notice that it's not a polynomial over a polynomial. This time we have a radical function over a polynomial. And notice also that the degrees match. The degree on top, since the square root of x squared is actually just x, that means that the numerator and the denominator both have a degree of 1. So we can look at those leading coefficients. The leading coefficient of the numerator is, remember, this is actually the square root of 4, which is 2, and this leading coefficient down here is 1. 2 over 1 is 2. So I know that y equals 2 is a horizontal asymptote, but since this is this radical function, what that means is there's actually 2 asymptotes, two horizontal asymptotes. There's one at positive 2 and one at negative 2. So what we need to decide is, as x is approaching negative infinity, which asymptote is this function, is this ratio approaching? Is it going to be approaching positive 2 or negative 2? So what we can do is just analyze the signs of the numerator and the sign of the denominator as x gets more and more negative. So let's think about, as x gets more and more negative, what is this ratio doing? Well, the numerator, as x gets more negative, we're going to always square whatever x is, and so even if x were a negative number, once I square it, it's going to be a positive. So what that means is that the sign of the numerator will always be positive. As x gets more and more negative. And then the denominator, as x gets more and more negative, the sign of the denominator is going to be negative. So, so now we have a ratio that is a positive divided by a negative, which of course that would be a negative result. So what that tells us then is that as x approaches negative infinity, we know that on the left end of this graph, the graph of this function is approaching negative 2. So we will say the limit as x approaches negative 2 of the square root of 4x squared plus 1 over x plus 2 is equal to negative 2 for our final answer.